Okay, so it says we're live. We're not actually live. Don't worry. Um, okay, yeah. Welcome everybody to another Cyphren interview. We've been on a formal verification roll right now, and today we're going to continue that with Karma from A16Z, who's been working on the Halmos tool, and we're very excited to have you here. Karma, how you doing?
Hey Patrick, I'm doing good. Thanks for having me on. Super excited to be here.
Absolutely. Well, thank you so much for being here. So Karma, what do you actually prefer to go by the way? Is it Karma? Is it Karma Coma? What is your
Uh,
preferred tag?
yeah, Karma works. It's short for Karma.
Short for Karma Coma. All right, cool. And then Karma Coma, that's your tag on Twitter, right?
That's right. Yeah, that's my like Web3 persona, I guess.
Web 3%. Okay, cool. Well, anybody who wants to follow Carmacona on Twitter, I highly recommend you do so because he posts a ton of very niche memes that are very funny, but you have to have a lot of context for them to be funny. Like he posts like formal verification memes and stuff, but like nobody gets them except for the few of us that understand, formal verification or fuzzing. But eventually, Karma, one day everyone will understand them, right?
I know 12 people understand my memes. So yeah, it's all good.
All right, cool. Well, Karma, yeah, just to jump into it. So you're working at A16Z as a formal verification security research engineer. Actually, what is your title there?
I'm a research engineering partner.
Research engineering partner. Okay, so
That's
partner
right.
is that a what does the part of it mean?
It's part of the investment firm terminology, but really like, what it means is my job is research and engineering, right? We have a research team and an engineering team, and I'm sort of spreading both.
Yeah, gotcha, makes sense. And what do you do mainly? What are you mainly working on?
Right now I'm really mostly focusing on Helmos, right? So improving the tool and communicating about it, and that's probably like 1/2 of the job. The primary part of the job really is helping portfolio companies, right? So basically working with other engineers, protocol engineers, right? People trying to like test or could be reviewing designs, architecture, pull requests, like incentive design, all these sort of good stuff at the solidity level.
So just anything a security person would be interested in. That's what you're working on.
Yeah, so I'm not just focused on security. We do have proper security people. Dejun, who I work a lot with, is very much focused on correctness. We have Matt Gleason, who's amazing at actual security, reviewing, auditing, looking for, vulnerabilities type of things. I'm more focused on protocol design and testing. So a little different. We all have different flavors that we're, focusing on.
So protocol design and testing. So I guess here's where my mental model starts to break down a little bit because I thought you were the lead maintainer of Halmos. And if you're working on Halmos and then you're also doing this protocol design, how are you balancing that? Is that something that you constantly struggle with?
It's about 50-50, yeah. So sometimes it's frustrating because I have some ideas. I have basically too much ideas and not enough time, right? So I have a bunch of things I would like to work on to improve
Mm,
Helmets, but also need to, help, these companies work on their protocol and because they want feedback, and it's also super exciting. But literally, my problem is that the days are too short, right? So
right.
that's the balancing act is just trying to like fit everything in one day, but there's only 24 hours, so that's the difficult part.
Well, thank you for spending some time here to tell people about what you're doing. I really appreciate it. So, okay, so spending 50% of your time doing protocol design, helping these projects just get better, right? The other 50% working on Halmos. So something that is really interesting to me. So we've spoken with, and we were talking a little bit about this before we started recording. We've spoken with Chandra from Certora, right?
Mm-hmm.
She's working on the tool, working on Certora, and their whole thing is form verification. We've spoken with um,
Palina.
Polina from runtime verification. Same thing. Their whole
Mm-hmm.
thing is formal verification. And now we're speaking
Right.
with you, and you're working at A16Z, whose whole thing is not formal verification, right?
Mm-hmm.
How does a formal verification tool play into A16Z's? Well, I mean, obviously, like you don't have to tell us the roadmap or anything, but yeah, how does it play into that, right? How does it make sense for an investment firm to have this arm?
Yeah, so I think initially the project was started about last year by Dejun, my coworker, and that's really because he wanted it, right? He needed a tool like that because he does a lot of auditing, right? And so he wanted a different kind of tool to help him basically perform essentially audits, right? Correctness focused kind of audits of like portfolio companies and their code bases. And I was not at the firm yet, and I saw that. I was like, wow, that looks really cool. And I started playing with it for CTFs, right? Initially, that's I got nerd sniped into Curta. I was like, hey, can I try to like use this tool to like basically solve the challenges for me because I know these are basically just too hard. And so for a smooth brain like me, I mean, if a tool can do it, that sounds very good.
Mm.
And I did, right? And so initially I was like, wow, okay, that thing actually works on like real problems, right? And so the idea overall of the tool is that we want to be able to like say interesting things about EVM bytecode in general. And so it's super interesting in all sorts of ways, right? So you have the CTF aspect is more kind of for fun, but it's also a nice way to benchmark the tool. Fundamentally, it's really also for bug finding, right? Like you're auditing the protocol and you want to get to those last bits, right? And you want to try to make sure either that it's retightened down or that you want to find some bugs, right? And so having solid tools to help, is nice. And that's already fuzzers out there, right? So we're taking a different approach, and we can talk more about that if you want. But it's not a matter for me of like which one is better. It's nice to have different tools that work differently, they have different strengths, right? And so yeah, for us it's really about can we help? It was researching our own initially, right? Can we help portfolio companies with this kind of tool that's a little different than what they're used to, maybe? And it's also like a research platform to some extent, right? We can, because it's in Python, because it's different, we can talk about the other tools if you want. We're taking a different approach, right? We're never going to be as complete as some of the other tools out there, but we're trying to be a little faster, a little more iterative, and sort of tailor the tool for different use cases. But yeah, the idea is essentially is like, can we try to help make protocols more secure with these kind of tools that's different from what we see normally?
Interesting. So you got nerd sniped into FE. I feel like that's kind of how everyone gets into form verification. They're like, wow, this is a really cool topic. Let me divert over there. So why did you choose? So you were working on CURDA, right? Which is a really cool capture the flag for anybody watching. Definitely go check that out. Why a formal verification tool to solve CURDA puzzles? The I got to move fast. I want to solve these. Like the quick in me goes, okay, I'm going to use a fuzzer. I'm going to do manual review. Why were you drawn to Helmos? Why were you drawn to this formal verification tool?
Right. But to some extent, what you can do is you can sort of disregard the whole formal aspect of it. To me, in my context, what formal verification means is it's a tool that knows how to reason about it's code that can reason about other code, right? And that's kind of difficult, right? You have all the halting problem and path explosion and all these kind of things. But really, fundamentally, that's what it is. It's a program that can ingest another program and say stuff about it, right? Which is kind of what we're trying to do, right? When you edit a code, what you're doing is you're running an interpreter in your mind, right? And if you're good enough and your interpreter is like feature complete, you can maybe find a little something that the others who are running a different emulator in their mind, they didn't see, right? And so to me, that's cool, and it feels good when you find something, but it doesn't scale, right, very much. So ideally, I would like to turn this kind of process into a tool, and that's where formal verification comes in. Is you need to define the interpreter in a way that can let the program reason about it, right? And so when we go to something like a CTF, we're trying to find a solution to a problem, right? You're literally asking the tool like, hey, here's a problem, give me a solution, right? And if the tool is good enough and you formulated the problem in the right way, it may be able to actually come up with a solution for you, right? It's kind of like instead of doing mental calculus, just use a calculator that works really well for that type of problem, right? So that's the idea here. Is like, okay, if you can use a tool that does this for you, why would you use your brain power on that, like do something else?
But why not a fuzzer then?
So I mean, if a fuzzer works for your problem, it's cool. Use that, right? The problem with the fuzzer is you're going to hit a wall at some point. So to me, like the strength of a fuzzer is if you're looking literally randomly, right, by definition. So what we're trying to do is you're trying to explore a search space for a problem, and some inputs sprinkled somewhere in the search space are going to trigger an issue, maybe, right? And so then the question is like, okay, you have a haystack and some needles, and so how efficient the fuzzer is going to be really is going to depend on the size of the haystack and how many needles you put in there. So if you have exactly one needle in a massive planet-sized haystack, the fuzzer is not going to work, right? But if you have like a bunch of handfuls of needles all over in a fairly small haystack, then yeah, like the fuzzer is going to go through it, and after a couple thousand runs, maybe you find something, and that's cool, right? But it doesn't scale much beyond that. Like once you go past, I don't know, actual numbers, but like even a million runs start getting a little expensive with something like the Foundry fuzzer. So if you're talking about like trillions of runs, like at this point it's hopeless. Like you're not going to find it. It's not a matter of just throwing more compute. That you're hitting the randomized, threshold. Basically, at some point, that's not going to get you anywhere. Like,
Right.
if you have one wrong value in all of the U into 56 space, it's just you're not going to find it, right?
So kind of the completeness of FV is something that is more exciting to you. You feel like kind of a random walk isn't good enough, is what you're saying.
Right. So random walk is cool, right? I mean, if you can find something quickly with it, it's great. Do that. But at some point, you will stop finding stuff. You will time out. And so then what do you do, right? So what's cool with something like FV is by reasoning about the actual semantics of your program, you take it from a different direction. Like you sort of turning inside out and say, okay, can I look at this and reason about the loops and the storage and the memory and the ABI, all these things. And maybe actually you can say stuff about it, right? You can say, well, no, this storage location will never be overwritten or this type of whatever is relevant to the problem. And once you've established that, you can move past, right? You can progress and say, okay, I don't need to spend days of compute on this. It's like I've proved it. I can move on to the next thing, right? So that's what's interesting for me. Is like if randomize works and you can pick something up quickly, it's all cool. But yeah, at some point you're gonna hit a wall, you're gonna time out, and you don't know. So and that's the real problem here is like once you hit a wall and you're not finding a bug, is it because there is no bug, right? Or is it because there is one, but it's just kind of too hidden, right? I mean, too rare, right?
This was part of your talk at the was it Dev Connect, I believe, right?
Yeah, the Solidity Summit. Yeah, exactly.
So everybody who is watching this should definitely go watch that. By the way, go watch Karma's talk. He talked about exactly this, right? Hey, if you use a fuzzer, great, you're gonna find issues, but you're always gonna have this question: are there any left? Exactly. Where what you're saying is, hey, formal verification, you do not have that question. Fuzzer, you will find bugs quickly, yes, but there will always be a small percent chance that there's another needle that you didn't pull out of the haystack. So cool, makes a lot of sense. So have you always had this mentality? What were you doing before A16Z? Have you always been like, oh, I want to work on these really cool complete? Yeah, what were you doing before A16Z?
Yeah, so there is a little bit of a cheat code there, which is I did a PhD in formal verification, but that was something like 15 years ago.
Cheat code. Getting a PhD is a cheat code.
It is, yes, it does help with this kind of stuff. So I do have a background in this kind of low-level semantics, trying to reason about logic and this type of stuff, and that's how I came to the US in the first place. Then I took a sort of long detour in basically Fang, right? So I got a job at Apple. I was doing compiler stuff there, super interesting, but much less academic, much more applied, obviously. Then I took another long detour at Netflix. I was doing distributed systems, so completely different things, just more like the craft of actual software engineering, learning distributed systems, managing incidents, the cloud, like pure Web 2 stuff completely. And recently, I sort of went back. I didn't go back. Actually, I picked up, Web3 and DVM skill, and I think it's going to probably be news to you. But I went through your bootcamp 2 years ago.
No way! Oh, which one?
It was 2021. Like summer 2021. 2021 is the year I decided, okay, I know I've been reading about the EVM, I've been reading about Bitcoin and all these things, sort of as a spectator,
Mm.
and I've tried some demos and stuff like that. At some point, I was like, okay, I need to learn this thing inside out. I want to learn Solidity and how the EVM actually works. And so I went through your smart contract bootcamp,
Oh,
and
badass.
I went
Was it
through the
the
yellow paper.
was it the brownie one or the hard hat one? It's probably one of the two.
Brownie, yeah, it
It's
was
Brownie.
good.
Yeah, Python. Woo!
Yeah, that's right.
No way. Oh, cool. That's so.
Yeah,
That's fantastic to hear. So, okay, you said so. Basically, you were like, all right, cool. Fang is cool, but like overrated. Whatever. Let's jump into this EVM thing. I'm gonna go check out this random dude on Free Code Camp who kind of talks kind of loudly about how much he loves
that's
Python and
right.
stuff. And now here you are.
Exactly, yes.
Oh wow, I love that journey. Oh wow. Oh, that's so exciting that you took the course. Yes, excellent, cool. Great. Okay, so now you're here. Now you're like, okay, I'm going to try Halmos on Curta, CTFs. Boom, did really well. I want to keep doing this. This is really cool. And now you reach out to Halmos, or Halmos reach out to you. Something happens. You start doing FE at A16Z.
Mhm.
You mentioned something a little bit earlier. You said Halmos is never going to be as complete as some of the other tools out there, and that kind of stands out to me. Why? I guess why did you say that? What is the goal of Halmos? If you know if you're
Right.
why why not? Why will it never be as complete as some of the other tools out there?
Well, just to give you an example, we don't do gas at all. Like there is not a single mention of gas anywhere in the tool. So that's one thing we just don't model at all. So if your logic relies on gas anywhere, we're not modeling it like
Mm.
literally, which means we cannot pass we're not a full EVM compliant interpreter, right? We cannot pass the tests that the regular Geth EVM has
Oh, and
because
then
we're not actually a full EVM, right?
right, and actually, hold on real quick before we keep going. So, for those of you who are unfamiliar with form of verification or symbolic execution, go back and watch the talk with either Chandra or Polina. We went over it a little bit more in one of those. So, that's your homework if you're coming to this with nothing. But sorry, yes, okay. So how much you're not doing any gas? You're also not doing
Right.
any. What did you say? You're not doing any EVM modeling. What was that last bit?
So yeah, just to give some idea. Okay, what is Hamas really? Fundamentally, it's an EVM, right? My previous project was small EVM, so the idea was like, hey, can we take the yellow paper, the PDF, and turn it into like a working Python small implementation just for
Right.
learning purposes? And Hamas to some extent is the same thing, just kind of more serious and more industry grade, but it's still at the end of the day just a Python interpreter for EVM bytecode, right? Um, but the way we interpret it, instead of executing it directly on your CPU, is we encode it into SMT formulas, right? And that's kind of where the magic of simple execution comes in. So we don't execute directly, we translate it, right? So you can think of it as a sort of transpiler in a sense, right? So we have SMT solvers out there like Z3 and stuff like that are great, and we sort of treat as a black box. But what they do, they don't know about EVM, right? All they ingest is SMT formulas. So basically complicated symbols, you feed it into them, and they come back with a yes or no, like does this work or does this not
Mm.
work? That's the job, that's what it is, right?
So Halmos is almost like so. Whereas Python is like an interpreted language, right?
Mhm.
It compiles, well, it takes your code and it figures out what you're trying to do and turns that to machine code. Whereas like something like Rust or C++ is compiled. It actually like takes it and goes, boom, here's the binary for this. Halmos is kind of similar to Python in this regard. You're saying it interprets it into this SMT language. And then again, for those who are unfamiliar, this Z3 is one of the most popular SMT languages for doing formal verification, right? It's a way to, it's like, you basically think of it as transpiling your code into a massive set of booleans
Yeah.
that can be like evaluated to true or false at the end. But so what Halmos is doing, you're saying it's almost, yeah, it's literally transpiler for SMT lib.
Mhm.
Are I don't know how much we want to talk about other tools here. I was under the impression that kind of all tools under the hood were using Z3, right? They're or not,
Uh,
some type of SMT lib, right?
yes. Yeah.
But you're saying they're not necessarily actually transpiling it. They are using Z3, but yours is almost kind of more of I don't want to say like directly, indirectly, but just taking it, translating it to Z3, running Z3, and then calling it a day.
I think we work in that sense roughly in the same way. I think so. We all use some kind of SMT solver as a backend, right?
Right.
Z3 is like very common because it comes out of Microsoft Research and it has like nice bindings in all sorts of
Mm.
languages, which makes it super nice to integrate, especially in Python. So if you're a Python developer, like you should really pick up on Z3 Python. It's super amazing. It's like it lets you type essentially natural idiomatic Python and then ask, hey, like solve this equation for me. So it's great for homework. It's great for all sorts of cool things.
Nice.
Not enough people know about it. It kind of feels like magic when you use it. You literally encode anything you want and you say, hey, solve this for me. Sometimes it will time out or return unknown because it cannot answer literally everything, but it does solve a lot of super cool stuff.
Hmm.
Anyway, so we use that as a backend. Most people use either exactly this one or something similar because it's easy to integrate. Now, I think the main difference is in the way we encode and what we choose to encode, right? So because we choose to not encode gas, for instance, we say, hey, we're a gas-free EVM interpreter in a sense, which means we can run bytecode forever. We will not run out of gas because we just choose to not model it because it's going to be more efficient. So what that means is the SMT formulas that we produce are going to be smaller, right? Because that's what we choose to focus on, right? I think so. I haven't looked at the internals, but I think control by runtime verification is probably a lot more complete. It will model the semantics like exactly one to one the way they're supposed to be interpreted. It can probably pass the whole EVM compliance test suite. So that's not a goal for us, right? I mean, so that it's important to understand the limitations of the tool you're using. And so our focus is like not producing false positives, but we can produce false negatives, right? Because we choose to not encode some things, right? If you ask us the question like, hey, can this ever revert without gas? We will answer no, it's not possible because we don't know about gas, right?
Right. Right.
But some of the tools may be able to answer that question and say, oh yes, actually, if you run that loop, 1,000 times, you will run out of gas, right?
Right.
But they sort of all work the same in that sense. Like they all take your EVM bytecode and somehow transpile it into something that an SMT solver can reason about
Hmm.
and start answering questions.
Gotcha. Interesting. I feel like I'm learning so much more. And it's Pythonic, which to me always just feels really good.
Right?
Big
Yes.
fan of Python stuff. Hence that brownie video that you saw a few years ago. So okay, cool. So the goal is, hey, we want to make this easy to use tool that is going to be that's going to kind of very quickly with really solid developer experience. We actually Karma was nice enough to actually jump on a call with me. I was having an issue trying to recreate this square root verification thing that I was doing. He jumped on and I was like, oh, this is so hard, like blah blah. And he's like, dude, you can just like run this command on one of your Foundry tests and you're good. And I was like blown away by that. I was like, what? And yeah, this very kind of developer friendly form verification tool where, as you're saying, okay, maybe it's going to miss out on gas or something, but what it's not going to do is it's not going to steer you wrong. Worst case scenario, it's going to tell you something breaks when it doesn't, just because you're not modeling gas, right? So that's the goal, is to have this very quick,
Alright, so now I'm going to check this Harness tool quickly, try to play a little bit with it and see how the formal verification works. Okay, so there is a interesting answer that you can regarding the square root function written in assembly. I found the almost telegram that Patrick Collins said that using Almos he was able to find a bug on the square root function, but he couldn't find this bug using fuzzing test, even running 1 million times. So for those who are interested, uh, I invite you guys to go on the Almos Telegram and make a research. I was reading it, so very interesting. I will try to dig a little bit more about this issue and try to run the Almos test on the square root function and then use it to make a report on the CodeHawk platform. Oh, well, I think this GitHub repository is very nice, but at the same time, it's giving all the answer regarding the challenge. I just found it, so I'm going to try it. So it seems that this library for the challenge was inspired by the Soladi square root function written in assembly. So I can see it's very similar. The difference is this part, this number is different from this number. Besides that, the whole logic is the same. Okay. This was just to check the code.
Easy to use formal verification tool. Is that kind of the goal?
Yeah, kind of. So, yeah, basically a couple design goals. So like not being complete. I mean, that's not a design goal. Being easy to pick up. That to me is the key, right? Is I want something like, just like Foundry. Right? I'm a Foundry power user, I guess you could say.
Yep, sure.
And I love it. And I love writing my tests in Solidity, right? And I love the cheat codes, and I love this whole interface, right? I don't want to have to deal with JavaScript or
Yes.
any of these other ecosystems, right? So I like staying within Solidity. I think it's super expressive. You can. It just feels natural, right? You write your code, you write your tests, you can iterate fast, no context switching. So we want, I mean, the tool was designed like that initially, but we're really sort of doubling down on this type of interaction model. Just because it's super readable, super expressive, so you don't need to learn a whole new thing, right? If you're already familiar with this type of testing, right, that's been popularized by DAppTools, I think initially,
right,
and then Foundry. I mean, it's great. You're already, in that ecosystem. You're already familiar with this type of stuff. It's super comfortable, right? So we're doubling down on that. So we want to, you don't need to, you literally don't even need to learn about anything about SMT or Z3. I mean, we're talking about it now, but to some extent, this is all abstracted away, right? That's what the tool provides for you. You write Solidity. We get the output of the compiler. All we know about is EVM bytecode. We don't actually know about Solidity even with a pure EVM bytecode tool, which means we can also test Viper. We can test Huff. All we care about is EVM bytecode, right? We turn that into SMTlib. We run Z3 on it for you, so you don't have to. And that's it. That's kind of the kind of iteration we have in mind. So having a good developer experience to me is like super important. Having performance as good as we can make it. So that's why potentially making trade-offs like gas and stuff like that. Being Python also means it's super easy to customize. That's what I did for the curl CTF. I was missing a feature, and because it's Python, it's super easy to just pick up on it, tweak something, use it as an API. I mean, that's why what I really like about Python is like how flexible it is. You can easily import it as a library, make some changes and customize it. So for this type of workflow, it's super, at least for me, it's super comfortable. And yeah, that's about it. Like, and no false positives. That to me is the other thing that's super important. If I run one of these tools, I don't want to go through like 10 warnings and only to find out that only one of them is valid and the other 9 I can ignore. Because you do that enough times and then you just kind of ignore everything, right? Your brain shuts off. That's another big design goal, is like we don't want to subject developers to this type of stuff. And it's kind of a strong constraint, right? Because potentially we may miss things. So we're sort of, there's a spectrum, right? You have security auditors and you have developers, right? They're potentially going to use the same tool, but they may not want the same thing out of it. And so I'm sort of taking, I'm putting the blanket towards the developer side there, right? Because to me, you can't subject the developer to false positives.
Right.
Maybe it's more okay on the security auditing side, because you do want to get that one valid bug, even if you have a couple invalid ones that you can filter. I'm not sure, but coming from the developer background, I know I just refuse to use a tool that gives me false positives.
No, same page, 100%. Cool. No, so I feel like I learned more about the mission of Halmos, kind of what you guys are doing, and yeah, this is all really interesting. So before we started recording, we were actually fiddling with how to share screen. I would love to share this video, but I feel like I'm ill-equipped to give the context of this. What's this video that we're going to show? What's the context of this video?
Right. So yeah, it's going to be a Cifrin exclusive because I haven't tried it yet. So
Woo!
all right. So here's the context. So we have really two big problems when we try to reason formally about programs. On one side, you have the path explosion problem, right? As soon as you have loops and branches, you can have many paths, and so it's just hard to like reason about this kind of volume, right? It can rise exponentially.